All right, so let's see. All right, so let's see what we got here. So any questions on the homework before we start? Because I want to just run through these. Yeah?
Well, I'm actually got a question about 7.3 number 2.
Okay.
Over that,
Let's start with that one.
I guess I didn't understand what the directions wanted.
Let's see what it says. So 7.3 number 2 says, let A be the set 1, 2, 3 and define f from A to A by, and it tells you what the function values are. So we've got the following setup. A is a set with 3 elements. And f goes from A to itself. And we're told f by being told its function value at each point in A. So 1 goes to 2, 2 goes to 1, 3 goes back to itself. And then it says find f squared, f cubed, f to the 4th, and f to the minus 1. And I put a note on Canvas when I posted the assignment that said, for 7.2 number 3, if f goes from A to B, then f squared is f composed with itself, i.e. f little circle f, same for f cubed, etc. So f squared is just f composed with f, and you're asked to describe what that function is. So the easiest way to describe a function, since it's given to you by explaining what it does to each point in the domain, is to describe what this does to each point in the domain. So let's look at f squared of 1. That's f composed with f applied to 1, which we can think of as apply f to 1 and then apply f to that result. So that's f of, and we know f of 1 is 2, and we know f of 2 is equal to 1. So f squared carries 1 to 1. F squared of 2 is f composed with f of 2, which is f of 2, which is f of 1, which is 2. And f squared of 3 is f of 3. And f of 3 is 3, so this is just f of 3, and f of 3 is 3. So f squared carries 1 to 1, 2 to 2, and 3 to 3. And you could write it like this, or you could write it as a set of ordered pairs, like this. And if we were using this notation, we could have written f as a set of ordered pairs. 1 goes to 2, 2 goes to 1, and 3 goes to 3. You could also express f squared by saying f squared equals the identity on set A, because that's what the identity does. It carries every element to itself. So then you're asked to find f cubed, which is really just f composed with f squared. And you can probably start to see what's going to happen here. So f cubed of 1 is going to be f of f squared of 1. And since f squared is acting like the identity, this is just f of 1, which is 2. And similarly, f cubed of 2 is going to equal f of 2, which is 1. And f cubed of 3 is going to equal f of 3, which is 3. And we could also observe f cubed is exactly the same as f. And we expect that because remember, the identity is a thing that when you compose with f doesn't change f. And since this is the identity, f composed with the identity is just f. And then f to the fourth, this is f composed with f cubed. And since f cubed is doing the same mapping as f, this is the same thing as f composed with f, which we already decided was the identity. And if you don't want to do those tricks, you can just work through this for f squared, f cubed, f to the fourth. Right, it's just a little more repetition, but it'll get you the same thing. And then you're asked to find f inverse. Can't do this on whiteboards. So f inverse goes in the reverse direction, so it still goes from A to A. And here's one way to think of the inverse. F of 1 equals 2, f of 2 equals 1, f of 3 equals 3. Well, this tells you that f inverse of 2 equals 1. F inverse of 1 equals 2, f inverse of 3 equals 3. In other words, f is changing this into this. So f inverse takes this and turns it into that. It undoes the mapping that f did. So if f of x equals y, f inverse of y will equal x. So f inverse of 1 is 2, f inverse of 2 is 1, f inverse of 3 is 3. That's exactly the same mapping that f did. So in fact, f inverse is the same as f. And you could write this, or you could write this, or you could put it in words. And this should make sense with the other results you got, because f is the same as f inverse, so f composed with f should be the same thing as f composed with f inverse. And an inverse is something that when you compose with the original function, you get the identity on the domain. So if you had done the inverse first, you could have immediately jumped to this fact that f squared will be the identity and so on. But I think it's better to work through it. So questions on that? Uh, 7.3, number 4. And this one looked pretty good when I glanced at it. So let's see what we have. S of n equals n squared. U of n equals n plus 1. And d of n equals n minus 1. And we're asked to find USD, SUD, and DSU. All right, so it's more function composition. So u of s of d so let's see what this does to n. So u of s of d of n is u of s of, and what's d of n? It's n minus 1. And what is s of n minus 1? And it can help to switch the variables around here if you like. So we could think of s of t equals t squared, s of w equals w squared, s of a box equals a box squared. So s of n minus 1 equals n minus 1 squared. And that's kind of the trickiest part of composition, is not getting tangled up with seeing the same variable. So is that step okay with people? And then what is u of n? It's n plus 1. U of x is x plus 1. U of this thing is this thing plus 1. Oh, I made it worse. Yeah, I'd really like, oh, okay. Cool. So u of this thing is this thing plus 1. Right, which you could simplify as n squared minus 2n. Plus 1 is going to be plus 2. But either way. And you just do the same thing. So s composed with u composed with d of n is s of u of d of n, which is s of u of, and d of n is okay, n minus 1. And u of n is this thing plus 1, so it's n minus 1 plus 1, which is just s of n, which is just n squared. And then dsu of n well, u of n is n plus 1, and s of n plus 1 is n plus 1 squared, and d of whatever is whatever minus 1, which is n squared plus 2n plus 1 minus 1. So again, the order is totally critical, right? You get completely different functions in general, depending on the order of composition. And this is just calling functions inside functions. If you wrote a function called s and u and d that returned its argument squared, its argument plus 1, its argument minus 1, and then you made a function that called s and inside it called u and inside it called d, right? Or if you actually just said s of u of d of n, right, you should end up with n squared. That's all the composition is doing. It's basically nesting these calls inside each other. So that was 7.3. Let's look at 7.2. So 7.2, number 2, 4, and 8. So question 2, all bijections from 1 to 3 into ABC. So what are all the bijective functions from 1, 2, 3 to ABC? Say again?
1, 1, A, 1, comma A.
Mm-hmm.
2, comma B. 3, C.
Cool. Any others?
Is there like a rule you can use to avoid writing them all out? Or do you just write them all out?
I would just write them all out. Should have done this in a different order. Any others?
Yeah, I only got 6 too.
I think there's only 6. How do we know if there's only 6? Well, the thought process I was doing in this at least was 1 has got to go to either A, B, or C, right? Suppose that 1 goes to A. Well, let's look at these. Suppose 1 goes to A. Okay. Now 2 has to go to either B or C. And once we've decided what 2 goes to, 3 has to go to the other one, right? So 1 could go to A either here or here, and then 2 can go to B, or 2 can go to C, and 3 goes to the other one. So you got 3 choices for where A goes to, and for each of those choices you have 2 choices where 2 goes to, and then you have 1 choice where 3 goes to. So 3 times 2 times 1. So in a few weeks we'll talk about counting and permutations and combinations, and we'll see rules for enumerating how many of these things there are. But that's one way to get there. And I mentioned this on a few homeworks. Right? This is not sufficient to express this function. Why is this not sufficient? Yeah, because this is exactly the same set as this. And if by this you mean 1 goes, or let's do it like this. Right? If by this you mean 1 goes to A and 2 goes to B and 3 goes to C, that's an underdefined definition because this is exactly the same set as this. Right? The order of the elements in the set does not matter. This is the same set as this. So you can't write this and say this is the definition of this function. But you can write, instead of this function, we could write 3 comma A, 1 comma C, 2 comma B. Is that the same function as this? Yeah. That's why we're using ordered pairs, because this is saying 3 goes to A, 1 goes to C, 2 goes to B. That's exactly what this says. And the fact that I listed 3 first over here and last over here doesn't change the function. Okay, so that's why you have to use ordered pairs when you write a function like this. So how many bijections from 1, 2, 3 into A, B, C, D?
Yeah, I said it wasn't hot.
There are no bijections from this set to that set. Why? Because none of your mappings can be surjective. 1 is going to map to one of these elements, 2 to another, 3 to a third, and one of these elements is going to be unmapped. It's not surjective, it can't be bijective. So there's no bijections into from a finite set to a finite set that's larger. But for infinite sets, that's not the case. Well, for infinite sets, that doesn't even mean anything. All right, what was 4? So 4 was asking about whether the following mappings were injections, bijections, or surjections on the set of real numbers. So let's just do 2 of these. So f of x equals negative 2x. So let's do injective, surjective, and bijective. So is this function injective? Right, the only time 2 x's have the same value of minus 2x is when the x's are the same, so that's injective. Is it surjective? Every number can be expressed as minus 2x. In other words, we can solve minus 2x equals anything for x. And since it's both, it's bijective. How about x squared minus 1? Is that injective? Yeah, it's not injective because 1 squared minus 1 is the same as minus 1 squared minus 1. So it's not injective. And why is it not surjective?
Well, I was just thinking that it's a parabola, and they never seem to be injective or surjective.
Cool. It's a parabola, which means it's got either a lower point below which there's nothing or an upper point above which there's nothing. So it's going to fail to be surjective. This is an upward parabola, so negative 10, there's no solution to x squared minus 1 equals negative 10 because that means x squared equals negative 9. And that's only got complex solutions. So it's not surjective and it's not bijective. All right, so you got the idea on those, right?
Can we do F?
Yeah. So f of s of x equals x cubed minus x. Cool function. So what do x cubes look like in general in a graph, do you know? Yeah, so it's got this like that kind of thing, or maybe this kind of thing, right? So it tends to grow on both ends, but it's got some little action going in the middle there. So that might give us some ideas. So injectivity is x cubed minus x equals y cubed minus y. Does that mean x equals y? Or is it possible there's two x's that have the same value here?
Wouldn't the solution be 0, -1, or 1 to solve for x in that case, if you set it equal to 0?
Let's see, so if x cubed minus x equals 0, x times x squared minus 1 equals 0. Yeah. So there's 3 x values that all give you 0, right? You only need 2 of them. That's enough to say it's not injective. And injectivity is kind of failing this horizontal line test, right? If you plot the graph and there's 2 points that have the same y value at different x values, it's not injective. What about surjective? If you believe the graph of it, it looks like it hits every point. But that might be kind of hard to prove.
Any odd polynomial should be surjective.
It should. So x cubed minus x equals some magic number m. So yeah, that's a little tricky to prove. You could go calculus on it. You could look for places where the derivative vanishes, and those are either maxima, minima, or points of inflection, right? So if your curve is x cubed minus x minus m, the derivative is 3x squared minus 1. And so that vanishes at exactly 2 points, right? Plus or minus the square root of 1/3, I think. And if you look at the second derivative, f double prime of x is 6x. So it's going to be positive at one of these, it's going to be negative at one of these.
There's nowhere where the derivative doesn't exist.
Say again?
There's nowhere where the derivative won't exist.
There's nowhere where the derivative won't exist.
So that means it's continuous.
So it's continuous. So we're getting way past discrete stuff here, right? But if you play around with this, right, you can convince yourself there's 2 points of inflection and there's no maximum or minimum, right? So if there's no maximum or minimum, that's enough to tell you it's surjective because it's continuous and it has no bound. So that one takes some thinking, and I wouldn't ask you to like prove that mathematically, right? It's a question on the definitions of these types of functions. So yeah, that's a quirky one. Say again?
That was not surjective.
That one is surjective, yes. All right, and 7.1, 1 and 2, so which of the following are functions? Characteristic functions. So characteristic functions we talked about. I don't know what this thing does. let's look at it. So we got two sets, and yeah, so there's not a whole lot going on here. So f, for example, is defined like this. Is that a function? It doesn't need to satisfy a whole lot to be a function. The two main requirements are, one, it's defined everywhere in the domain, and we do have an ordered pair where the first number is 1, 2, 3, and 4. And two, it's got to take each point in the domain to exactly 1 point. Can't take it to 2. So this is a function. But let's just write a bad function. Right, this is not a function because the points, oh, my bad. This is not a function because it's saying the point 1 is associated to both A and C. Right, so it's trying to take the single point in the domain to two different points. It's not a function. It fails the vertical line test. All right, so 7.3, I also asked you to think about, 7.2, I asked you to think about some questions. So 7.2, number 6, 10, and 14. So how many people thought about these? Woo, cool. If I had not told you they weren't going to be graded, would you have thought about them? Probably. So let's see what these say. So 7.6, in your own words, explain the statement. The set of integers and the set of even numbers have the same cardinality. So what does that mean? Who wants to venture a description of that? Yeah.
There's a way to assign the values such that you can assign one from one set to an integer.
Yeah, you're doing right. So integers and evens.
Integers, so you can assign every even integer to an integer.
Okay, and vice versa.
They're both the same size.
Right, exactly. So saying that two sets have the same cardinality means that for every element over here, we can identify an element over here, and vice versa. What kind of mapping is that, where each thing over here goes to one thing here and vice versa?
Bijective.
It's bijective. So there's a bijective map from one set to another that makes them the same cardinality. Same with the odds and the integers, or with the evens and the odds. Every even can go to itself plus 1. Every odd can go to itself minus 1. That's a bijection between the set of evens and odds. Right? Every number can go to itself minus 1 divided by 2. That gets you from odds to all integers. So cardinality is about this one-to-one mapping between sets. Okay, and since we're talking a lot about countable sets, we use that term to say cardinality of the integers, we can think of a countable set as one which we can put into a one-to-one correspondence with positive integers. And as soon as we make that correspondence, whatever we map to integer 1, we can call that the first element. Whatever we map to integer 2, we can call that the second. So it's kind of saying we can place an ordering on these sets members such that we can identify a first and a second and a third, and every element is guaranteed to be the nth element somewhere in this sequence, right? For some n, it might be the millionth, but it'll be accounted for somewhere. So when we say a set's countable, we mean it has the same cardinality as the integers, which is that aleph naught symbol. All right, well, using that, let's look at question 710. So 710A wants us to prove that the set of finite strings of zeros and ones is countable. Prove the set of finite, so I'm going to say finite length strings of zeros and ones is countable. In other words, has the same cardinality as the integers. So,
Because I thought it was saying like infinite strings of any combination of 0 and 1.
so
That's not true.
So it says finite strings is the wording it actually used, so that means a finite number of zeros and ones.
But it's like any combination?
Any combination of zeros and ones, so this and 10 billion other ones and zeros followed by this. All of those are in our set. Okay? There's nothing in our set where we have an endlessly repeating pattern of ones and zeros. For example, the number that contains a 1 just followed by an infinite number of ones without end, that's not part of the set. But any string with a finite length where that string is composed just of combinations of zeros and ones. So if these were letters in our alphabet, right, our dictionary would be infinite, but we want to prove that it's countable. It's not too big infinite. And as computer scientists, you can do this with one sentence, maybe two. So any ideas? Yeah,
Maybe something with binary representations?
perfect.
What if it starts with a bunch of zeros? Then how would you handle that?
Oh yeah, that's true. Because I was thinking if you assign a binary number to the 1, but then there's also the extra case where you have 0, 1
Okay.
and 0, 0, 1. So just assigning binary numbers to the integers isn't enough. Because those are all in this set.
So all of those have to be in the set. We got to account for all of those. I hadn't thought of that either. So that's a good detail there. So how can we deal with this? Be lazy.
So how can we prove that it's bigger than infinity? I've never quite.
Prove that what's bigger than infinity.
Well, if we prove that this set of strings is larger than the set of integers, I shouldn't have said infinity. If
It's okay.
How do we prove that something's bigger than the set of integers? Because if we can prove that, we can prove this is false. You know?
So the only thing that we've proven had cardinality bigger than the integers was the reals. And we did that with that Cantor diagonalization trick. Remember that?
Oh, could you do something similar here and say, like, for every finite length string, there will always be one more with an extra 0 on the end?
Well, let's see what happens if we try to do that. So if we take the nth digit and we just toggle it in the nth number, then what are we going to get? So that's a proof that as it stands, we have a problem, but there's a way to fix this, and the way to fix is going to break that diagonalization proof.
Okay.
Because otherwise, we should be able to diagonalize. We should be able to say, okay, give me a new number where the first digit is the first number with the first bit flipped. The second digit is the second number's second bit flipped. The third number is the third digit is a third number's third bit flipped. And we should be able to construct this magic number and say it doesn't match any of the numbers because the nth number differs in the nth digit. But we got to do something, right? We haven't yet said that we believe this is countable. And in our demonstration that it's countable, we're going to do something that breaks that. So any idea how to show this is countable? So let S be any finite string of zeros and ones. Map S to the integer with binary representation. 1 followed by S. So tack a 1 onto the far left side. And now this will map to the number 3, this will map to 5, this will map to 9, and they'll all map to different elements. And that will break your diagonalization, because the 6th digit of this number, right, will get changed to a 1, that's fine. But when we're done, we're going to end up with a number. Well, let's see, how does that break it?
Because if there's always a good at the right, or 1 at the right.
Doesn't have to be, but yeah, if there is.
Well, it matters if it's a 0, but if there's 1 at the right, then it's always significant. All of the bits are significant.
Mm-hmm.
And as long as they're significant bits, they map to something unique.
Right.
Therefore, they all must map to something unique.
True.
Except maybe 0.
Yeah.
But you can just minus 1.
If you add a 1 onto the end of every single combination, whenever you toggle it back to 0, it's something that you've already added. So you can't use like your or not your end, but you can.
Oh, the reason we can't diagonalize on here is because this number we're constructing that's not going to work is going to have an infinite number of digits.
Yeah.
It's not going to be a finite length string.
That's true.
With real numbers, we didn't have that problem because we didn't require that the number of digits in our real number was finite. Even if we restricted it to be between 0 and 1, we allowed the string of digits to carry on forever after the decimal point. So it's really the finite length of each string that's saving us here. All right, so that's kind of a cool problem. This is why I gave these, because I think they lead to.
But this last one that had more. What was the third one? I'm sure
With which?
The one you were about to introduce.
Number 10. Prove that n cross n is countable. So that one we've actually done. So what does n cross n look like?
Rational numbers.
Looks like the rational numbers. Because n cross n is just pairs of 2 natural numbers. And our positive rational numbers are just pairs of 2 natural numbers, the numerator and the denominator. So we can do that kind of sideways maze running thing to get through all of those.
That's an interesting way to do that.
Yeah.
Because by proving they both use a pair of things, because this one is that one, their size is equivalent.
Yeah.
That's interesting. Oh,
So what about the set of all functions on integers? Prove that that's an uncountable set. So the set of all f from integers to any real number. Is that uncountable?
although originally I said it was a similar problem with the real, because not the real, the one Q.
Rationals.
Rationals.
Yeah.
Because you're always able to add one more
Mhm.
to the function, and you get a unique thing, kind of like how you're always able to add one to the denominator, a unique thing, without adding to the numerator.
Right.
But that's not enough to prove it, because we know that that's countable.
So what if we just do this? Define f sub x, which is a function from the integers to the real numbers, with the property that fx of any integer is equal to x. Is that a function?
Yeah.
Right? It's certainly inside this set. The set of all of these is a subset, but how many of these functions do I have? The same number as I have real numbers. Any real number defines a new function from z to r. And since I have an uncountable number of reals, I have an uncountable number of functions of this form. And that's just a small subset of the space of all functions. So this is certainly uncountable.
Fx
Yeah. But let me leave you with this in the last 30 seconds. The set of finite length strings of zeros and ones is countable. The set of functions into the reals is uncountable. What's the cardinality of a program sitting in your computer's memory? Is it countable? It's a string of zeros and ones. It's finite length, right?
Yeah, that's how I was trying to clarify. I wasn't sure if you were doing based off the computer memory or just a number of zeros and ones.
Yeah. So you could do it off the executable code, zeros and ones. You could do it off the ASCII codes of the C program itself. There's a countable number of C programs. There's a countable number of executable programs. There's an uncountable number of functions. There's functions we can't write. There's programs that we can write that generate real numbers. There's some real numbers we cannot print with a C program.
I'm not sure that proves that. Like, I get what you're saying.
We can talk about it Monday because we're 2 minutes over, but think about that. The idea that there's some real numbers we can't write with a C program, no matter how clever our code is.
I can understand you saying we can't have written all programs.
True.
But some programs, the mapping resource, like, we can just say, I'm gonna write that program now.
Sure.
Choose a random one.
Yeah.
We can write it.
I mean, we can write a program that prints the square root of 2. It takes forever to finish, but it will print out all the digits. We can write a program that will print all the digits of pi. If we keep it running, it'll keep printing more and more digits. But somewhere there's a bunch of real numbers that we cannot print with a C program. There's got to be, because there's a larger cardinality of real numbers than there is a cardinality of all the C programs in
I guess that's true.
the world.
That looks like a notification
Yeah.
from
Say you can print.
And that should be disturbing,
Say you can
right?
print every.
And then if you think of our brain as sort of a state machine with a finite number of states, that's really disturbing, because there's numbers we can't even think of, just plain old real numbers.
Say you can print every one of them, but say a code or a program